welcome back. Let us continue the discussion on the turbulent scaling. So, we are looking at the effect of buoyancy, and we derived the governing equations like continuity, momentum and the temperature equation, and we have seen the extra term which comes because of due to the effect of buoyancy. Now, we are looking at the buoyancy production and destruction. This is the one, if you have a parallel plate, and then this part is where you get buoyant production, and this is the buoyant destruction. Now, we can look at for this plane channel flow, this is a plane channel flow, we can look at the buoyancy versus shear. So, buoyancy versus shear. So, now turbulent kinetic energy budget for this fully developed plane channel flow with equal heat flux at bottom and top, we get like u prime w prime del u bar by del z, z by theta naught plus del z z of minus w prime half ui square minus 1 by rho p prime w prime plus nu del k by del z, and the last term that you have nu del ui prime by del xi, that is square. So, this we can rewrite in a different form like 0 minus w prime u prime, or one may follow the similar convention like u prime w prime del u bar by del z into 1 minus r I f plus del z z of this whole term here and minus this term. So, this particular term one can see is then this is where the r I f is the g w prime theta prime by theta naught divided by u prime w prime del u bar by del z. This is the flux Richardson number. So, one can also categorize if RIF less than 0, then we get buoyant production, and if RIF greater than 0, you get destruction, buoyant destruction. Now, net turbulent kinetic energy production if R I greater than 1, which is the upper bound of that. Now, we can see this effect of buoyancy on overlap region. So, you can think about this is an atmospheric boundary layer where in the overlap region is the region between your inner layer and the outer layer. So, the turbulent shear stress can be approximated at shear stress, basically this is shear stress at earth surface, which can be rho u tau square, and the turbulent heat flux which is rho Cp. This is the heat flux at earth surface, which is rho Cp E theta s, or rather F theta s. Now, if the buoyant effect on mean velocity is small, which is a neutral boundary layer case, then the mean velocity in overlap region one can write by u tau del u by del z equals to 1 by kappa, which is going to give you minus del u bar by del z equals to u tau cube by kappa z. Now, in this case the flux Richardson number in overlap region will be equal to G W f by theta naught by u prime by del z, which is G f theta s by theta naught u tau cube by kappa z z by L, where L one can define u tau cube by kappa g f theta s by theta naught, which is also called Obukhov length. So, that is how you can get these things. Now, similarly, one can look at the buoyancy effect on overlap region, which is an atmospheric boundary layer 2. Now, if the buoyant effect on mean flow is not small, so previous case we said it is small, then an additional dimensionless group appears. So, which is like z by u tau del u bar by del z equals to phi of z by s. This is where z by L is essentially the buoyant production or destruction to the shear production. So, that is the ratio of these two is the z by L. Now, if L greater than 0, it is in buoyant destruction, because your phi becomes 1 by kappa 1 plus 4.7 z by L, where using that you can get the mean velocity profile like that. And if L less than 0, this is the production. So, one can plot this, in this axis is ratio z by L, and look at this function phi, how this actually varies. Now, another situation which may appear is the neutral atmospheric boundary layer, where you can have this limit phi by z by L would be 1 by kappa in overlap region. Now, typically atmospheric boundary layer, this length scale is quite high. So, the atmospheric conditions are approximately neutral for z less than 1 meter. So, if that is the situation, one can now we recap our statistical description, where we had these Rand's equations. This is continuity, this is momentum, and this is Reynolds stress term. Now, here we got one continuity equation, 3 momentum equation or 3 component of the momentum equation. So, total we get 4 equations, but we got here total 10 unknowns like P, Ui, Uj prime. So, basically 3 velocity component, 1 pressure component 4 plus 6 Reynolds stress component. This is 6 component, this is 3 and this is 1. So, total it lead to 10 unknowns. So, we need closures, otherwise we cannot solve this system of equation. Now, if we rewrite the Reynolds stress term, that is Ui Uj prime, which is minus 2/3 rho plus rho Ui prime Uj prime 2/3 kappa delta Ij Kij. this term is isotropic part and this is the deviatoric part. So, this is essentially your turbulent shear stress and this is turbulent pressure. Now, using the turbulent viscosity hypothesis, so we have closed this term like this deviatoric part or turbulent stress part K delta I j equals to rho nu t del u bar by del x j plus del u j by del x I, and nu t here is the turbulent eddy viscosity. So, if you recall the scaling of that thing, so this is an velocity profile, and if this is the size of the eddy, the velocity scale would be UL. So, turbulent viscosity has the dimension of velocity into length scale. So, from nu t we can say that it would be of order of u naught and L naught, and this u naught and L naught for scale of large eddies, and this is if you scales of the mean flow, this would be of u and all L. So, it actually the eddy viscosity scales of the order of this velocity and length scale. Now, we can come to the hypothesis. So, in analogy with molecular stress allowed, a closer look at the molecular using kinetic gas theory. So, if you consider a one dimensional velocity profile, so this is at the macroscopic level and this is what happens in the microscopic level, the molecules. So, macroscopic momentum flux across this plane is sigma xy, which would be proportional to Cn m. So, this is the number of collisions across y plane per unit time and area, and these component contribute to average transfer of x momentum from collisions between molecules at y plus lambda and y between this. So, using the Taylor expression, one can write this sigma xy in terms of this and then lambda del u by del y, where L is represented like this. Here lambda is the mean free path, C is the mean molecular speed, m is the molecular mass, and n represents the number of molecules per unit volume. Now, in practical application, typically lambda is quite small than L, which signifies that sigma xy would be rho nu del u by del y, where nu is half of C bar lambda. Now, for air you can have, for example, air this lambda is approximate 60 nanometer, C bar is roughly 450 meter per second, which get you nu as 1.35 into 10 to the power minus 5 meter square per second. Now, then we get the model for turbulent viscosity, where lambda is scale, C bar goes to u naught, where nu t is scale like u naught into L naught. In general, this L naught is of the order of L for both boundary free and wall bounded flows. So, that means the turbulent mixing is non-local. So, this turbulent viscosity hypothesis still provides an reasonable result, in particular when production and viscous dissipation rate of Tk in local balance. Now, that will actually paves the way for building up the turbulent eddy viscosity or turbulent viscosity models. So, simplest one can think about, it is a constant turbulent viscosity. So, you simple jet like this, where nu t is u naught y half by R e t. So, the simplest one has a limited range of applicability, only boundary free shear flows. Now, model is incomplete, value of R e t is sensitive to define u naught and y naught. and also it does not account for the intermittency. So, that way the nu T, if you take a factor for intermittency ahead of this, which will look like this. So, this intermittency will give you the probability that at a fixed position x the flow is turbulent. So, some sort of an, now in 1925 way back, the Prandtl proposed the mixing length model, which is like nu T equals to Lm square magnitude of del U, and then later on in 1963 Smagorinsky generalized that and says that nu T would be like this, where Sij is the strain rate tensor, and you can look at this where this model can be, and later on also Smagorinsky used this hypothesis to derive the some other turbulence model. Now, then the development moved to a one equation model, where the model in which turbulent kinetic energy is used to estimate characteristics velocity scale. So, this is the example of Prandtl one equation model in 1940, where nu T is approximated like this constant root over of kinetic energy Lm, and this is the kinetic energy equation that used to be solved, where these are the model coefficients. Now, this model has a good agreement with the DNS in outer layer of the turbulent plane channel flow, but it fails in viscous wall region. So, it is incomplete since mixing length has to be specified. That means, this particular term Lm, which needs to be specified beforehand when you start your calculation. So, you need to specify that, and which creates the problem here. Now, later on there is the development moved ahead, and we have got two equations model, where simple two equation model you solve k and epsilon model, while kinetic energy and along with the dissipation, where nu T is approximated like C mu k to the power 3 by 2 by epsilon, which is C mu k square by epsilon. So, this was proposed by Jones and Launder in 1972. Then different variant of model like k omega, where you solve for kinetic energy and the turbulent frequency. In that case, nu T equals to C omega k to the power half by omega, where C omega k by omega. This is proposed by Wilcox in 1993. See, this two equation models are complete in the sense that no flow dependent specification like such as Lm is required. So, that way they look complete, where you solve for the kinetic energy or epsilon or the turbulent frequency. So, typically these days, even in the industrial application, these models are quite heavily used. Now, how we actually look at the relationship between viscous dissipation rate with the entropy. So, viscous dissipation is given as nu del u prime by del x j, which is nu omega I prime square plus nu del to u I prime u j prime by del x I del x j, where omega I prime square by 2 is the entropy. So, the entropy is a measure of the, so this actually the measure of the intensity of vorticity fluctuation. So, now one can see in the small scale you get to see the largest amount of this contribution of entropy and contribution of the turbulent kinetic energy at the large scale. Now, for wall bounded flows, shear flows, wall bounded shear flows, outer layer you get this dissipation is somehow connected with entropy like that. So, that means this equation can be approximated as the equation for entropy. Now, there is a paradox from Kolmogorov in 1941 that epsilon is actually determined by the energy transfer rate at large scale, and thus it should be independent of viscosity. But when you look at this, they are sort of correlated. So, then we get the transport equation for epsilon, where we got turbulent kinetic energy, which is del k by del T uj del k by del xj P plus del xj nu T by sigma k plus nu del k by del xj minus epsilon. Similarly, we get the equation for epsilon, which is del epsilon by del T plus uj del epsilon by del xj production term plus del xj nu T by sigma epsilon plus nu, that would be del epsilon by del xj minus dissipation term. So, there is a production term, there is a dissipation term. So, there are some empirical relation for that. This difference of these two is approximated as epsilon by k C epsilon 1 P minus C epsilon 2 epsilon. Now, if P increases, kinetic energy increases, so turbulent kinetic energy transferred down. Now, energy cascade at time scale k by epsilon, which will if your epsilon increases, so which will tends to decrease turbulent kinetic energy. So, now that is a two equation model where you have k and epsilon, and if you put everything together, this is what you need to solve in a Rand's context, where the first equation comes from the continuity, second equation is your momentum, this is for turbulent kinetic energy, where P is the production of kinetic energy, this is epsilon, where these are some of the model constants. So, that is a complete model, and now this is quite readily available in any commercial CFD package or code, or also most of the code which are used by the academicians also. Simple to use, easy to implement, and can be used for a wide range of flows with their limitations. So, one has to know the limitations. Now, if you look at those coefficients which are present there in the k epsilon model, so they are been determined by tuning the model for different flows. Now, one important flow is the decaying homogeneous turbulence. So, turbulence is absence of mean rate of strain. So, there is no production of turbulent kinetic energy, turbulence vanishes. So, that is why these are the coefficients are which are kind of looking at a different flows. These coefficients are tuned over a period of time, and they are now these coefficients are somehow one can say widely acceptable for large number of flows. Having said that, one has to make a note here that any specific application, this requires some tuning. Now, behavior of this model in logarithm layer for let us say plain channel flow. So, if you look at the behavior, so u tau square would be like C mu k square by epsilon, and this would be P minus epsilon and epsilon by k C epsilon 1 P minus epsilon to epsilon plus del y of nu T by C sigma y. So, this term which we will get back as minus epsilon by k C epsilon 2 minus C epsilon, and this is the turbulent diffusion term, diffusion transport epsilon from wall region towards the log region. So, this would be net sink term. So, using u bar equals to or u tau by kappa ln y by y naught, one gets C mu equals to u tau square by k whole square, which is 0.09, C epsilon 1 equals to C epsilon 2 minus square by sigma epsilon by C mu, where for kappa equal to 0.43, that gets you C epsilon 1 is 1.44. As I said, these coefficients are widely acceptable. Now, if you look at this performance of this model, so you require special treatment in the viscous wall layer, approximately value of sigma decreases for y plus less than 50. That means, if you go to outer layer, it is fine within that. So, lot of modification have been proposed. People have looked at the experiments and a huge set of DNS database of channel flow to look at what kind of modification to be made for this model to be accurately used in the that near wall region. Now, then after that, there is another set of model which is called Reynolds stress model, which is slightly more involved. Here the whole idea is that instead of using Boudien's hypothesis, we solve for the transport equation for each Reynolds stress, and now each Reynolds stress means we get so many equations for the 6 equations for this Reynolds stress term. And how do you obtain that equation? You subtract the mean momentum equation from the momentum equation, multiply momentum equation for ui prime with uk prime, similarly multiply momentum equation for uk prime, and two equations together, and once you take the Reynolds average, this is what you get. So, this is your each Reynolds stress component unsteady term. So, this side you can think about the material derivative of that. These two term altogether contribute to the production, and this term contribute to the turbulent viscous transport. See the pressure term, this is the pressure strain term, and this is viscous dissipation. So, essentially your left hand side, this is the material derivative of the Reynolds stress term or the stress component, where right hand side you have production, turbulence plus viscous transport. So, if you look at compared to two equation models, this equation set of equations are quite exhaustive. So, they are not that straightforward to be implemented, but it has certain advantages over the two equation models. So, like one can think about, there is no closure which is required for production term, that is one of the important aspect of it. Then one can think about isotropy of the microstructure except close to the wall, which can be approximated as ui prime del uk prime by del xj, which is minus 2/3 epsilon delta I k. Then there is a negligible contribution of microstructure to Reynolds shear stress. So, viscous dissipation rate of the Reynolds shear stress can be neglected. Now, there are other closure problem. So, like turbulent transport, that is one issue, pressure strain term, that is another problem, because it is responsible for return to isotropic and destruction of Reynolds stress term, and also it is computationally expensive. So, we will see how other terms that affect this Reynolds stress equation. So, we will stop here today and continue in the next lecture.